Okay, so you remember the Boston Dynamics handle robot? Well, back in 2017 they built this absolute beast of a balancing robot, and while I was in lockdown I wanted to build my own version, so I've created a mini version of the handle robot, and I've open sourced all the parts so you can build your own too. So, after finalising the initial design, I had to go to CAD and make the 3D model, and this was a problem because I didn't know what I was doing. So after I'd failed on the first attempt 3D printing, it was bulky, heavy, it just didn't work at all. I had to redesign the entire thing. Looks pretty good, time to print. So anyway, that's how I ended up with MABEL, or Multiple Axis Balancer, electronically levelled. In some of these initial tests, you can see that this is the design I actually managed to get balancing, and although it was a little bit shaky, it showed some promise, and I managed to tune this out later by altering the PID algorithm, but I'll get onto that in a minute. So by now you're probably wondering, how does the robot actually stay balanced? Because of course, without power, it would just simply tip over. So to combat this, we use a PID controller, standing for Proportional, Integral and Derivative. This allows us to calculate an error provided from the data of the accelerometer. So basically, we want it to stay upright, which is 90 degrees in our case. So many times a second, the PID controller is going to look at these values and decide the best course of action to the motors, and it's going to use that correction to stop it from tipping over. So if the robot wants to drift forwards, it's going to drive forwards in order to combat that, and the same if it's reversing. As the PID controller looks at the error of the values and uses the proportional, integral and derivative constants to make a change to that data, and then accordingly make a correction value that is suitable. So to tune the PID controller, we first need to choose some initial values. We first need to start by altering the P term, or the proportional term. And if this is too high, it's going to start overcorrecting. And so it's going to go wiggle backwards and forwards, go backwards and forwards, and it's going to tip over. It's just going to force itself over if it's too high. But if it's too low, it won't balance at all and it will just tip over. So this is the thing we want to get just right. At this point, we're not looking for it to react when it's being pushed, we just want it to be stable when it's not interacting with anything else. And so once you've got that pretty stable, or it's able to balance somewhat, then you want to move on to the I and D terms, or the integral and derivative terms. And the derivative, that helps us tune out some of the shakiness. So we want to tune this just right so that it's not shaky, it doesn't oscillate too much, and it recovers quickly when pushed. And the integral, this we want to just use this in combination with the derivative term, and the integral is just going to make sure that when it gets pushed, or when it gets interacted with another object, it's going to recover quickly and it's going to stop shaking quickly. So we can tune these out. In some of the tests, you can see that the derivative value was too high and it shaked a lot. And later, when I made this a smaller value of derivative, it wasn't as shaky and it was a lot more stable. So here's the Arduino and CNC shield stack here, look. These are the wires to the accelerometer, so the Arduino on the bottom there is reading that data, so like 50 times a second, and that's being processed in the PID loop, and it's going to send a correction value to these drivers here. And so that is going to tell the motors down here to, if it's going to go forwards, the motor is going to drive forwards to catch the robot, and if it's going to go backwards, it's going to drive backwards like that. It's a bit shaky at the minute because the top's not on and it's not completely balanced, but you get the basic principle. Now you might not think that moving the legs in a straight line was a difficult task, but it was actually more complicated than it might seem. And this was because of the fact that the different leg components are different lengths and sizes. So each servo must be driven at a different angle in order to move to the correct coordinate. To do this conveniently, I wrote a simple inverse kinematics program which uses trigonometry to calculate the best angle to move to any specific set of x and y coordinate. This makes it a lot easier to move to any specific coordinates without having to calculate the angle each time, or worse, just set an angle without knowing which coordinates to move to. The last core principle I want to talk about is probably the most counterintuitive, and that's the fact is that when you have weight at the top of an inverted pendulum system, like a balancing robot, it actually becomes more stable and easier to balance, like I'm trying to do here with my drumstick. Normally, when you build something, you want the weight to be as low as possible, and that means it's more stable, but in this case it is inverted. It actually gives us more time to react and easier to balance when the weight's at the top. Unfortunately, I could neither do that or balance my drumstick on my fingertips, so I'm having to record the voiceover separately. So the next steps for MABEL, I'm thinking that it would be really great to actually get the legs moving in a useful way, not just up and down. I'd really like to use a second PID controller to make it more stable travelling over rough terrain, and I think adding some arms eventually as well would be really cool. Apart from that though, I'm happy with how it's driving and stuff like that, but I'd really like to make the PID controller even more stable because it is still a little bit shaky at times, but I think this could be tuned out quite easily. And lastly, I'd like to say thank you to everyone who has supported me building the robot and the Raspberry Pi Foundation and Pi Wars, and just everyone who's given me feedback throughout the course. If you've enjoyed this video, I'd really appreciate a subscription, as I'm thinking about doing more of this stuff in the future. And also, if you like this video, give it a like, and basically, yeah, that's it. I hope you enjoyed my video, and I hope you want to see where MABEL goes next.